Good morning. Today we are going to discuss about AVL trees. AVL trees are height balanced binary search trees. Let me first explain about what is a binary search tree. A binary search tree is a binary tree that is either empty or in which every node contains a key and satisfies the following conditions. The key in the left child of a node is less than the key in its parent node. The key in the right child of a node is greater than the key in its parent node. The left and right subtrees of a node are again binary search trees. No two entries in a binary search tree may have equal keys. AVL tree is a binary search tree in which the difference of heights of left and right subtrees of any node is less than or equal to 1. The technique of balancing the height of binary trees was developed by Adelson, Velsky, and Landis, and hence the given the short form as AVL tree or height balanced binary tree. Observe the following binary search trees. There are three binary search trees. In the binary trees, every node contains a key and associated with a balance factor. Figure A is a height balanced binary search tree, so it is a AVL tree. Figure B and C are not height balanced trees, so they are not AVL trees. AVL tree is a binary search tree. AVL tree is a height balanced binary search tree. Every node is associated with a balance factor. Balance factor is the difference of height of left subtree and height of right subtree of that particular node. Balance factor may be -1 or 0 or 1 in an AVL tree. Insertion or deletion or search will be performed in less time in AVL trees comparing to binary search trees. Let us have an example of height balanced binary search tree. The following tree is a binary search tree. Every node is associated with a key and a balance factor. Balance factor is the difference of height of left subtree and height of right subtree of that node. In an AVL tree, the balance factor may be -1 or 0 or 1. The balance factor should not be more than 1 in an AVL tree. The balance factors shown in the above tree are not greater than 1. So, the above tree is a height balanced tree, that is an AVL tree. Let me explain another example of an AVL tree. Observe the binary tree in the figure. It is a binary search tree. All the nodes are associated with a key and a balance factor. The balance factor is the difference of height of left subtree and height of right subtree of that node. The balance factor of any node is not exceeding 1. So, it is an AVL tree, that is height balanced binary search tree. What are the advantages of AVL trees? Let me explain this with an example. Observe the two trees specified in figure A and figure B. Both are binary trees. Both are binary search trees. The first tree is a height balanced tree. The second tree is not a height balanced tree. Both trees having the same keys, same number of nodes. Key values are also same. Both are binary search trees. Now, if we wanted to search for an element 35, in the first binary tree, it takes two comparisons to find the position of node 35. In the second binary tree, it takes 6 comparisons to find position of node 35. Searching of an element is in a height balanced tree takes less time. Not only searching, insertion and deletion also will be performed in less time in height balanced trees, that is in AVL trees, comparing to normal binary search tree. This is a main advantage of using an AVL tree. Let me explain about AVL rotations. Using AVL trees, we can access nodes quickly. The processing time to insert a node or to delete a node or to search a node will be less comparing to normal binary trees. So, a normal binary search tree can be converted to AVL tree using simple rotations. Every node in an AVL tree is associated with a balance factor. Each time you insert a node, or delete a node from an AVL tree, the balance factors of nodes of AVL tree will get readjusted. Even after insertion of a node or deletion of a node, the AVL tree should maintain the property of AVL tree. That is, the balance factor should not exceed 1. If the balance factor is not -1 or 0 or 1, then we need to apply the following rotations to make the tree balanced. Even after rotation, the tree should maintain the property of binary search tree. To balance itself, the AVL tree may perform the following 4 kinds of rotations: left rotation, right rotation, left right rotation, right left rotation. Left rotation. Let us discuss about left rotation. If a tree becomes unbalanced when a node is inserted into the right of a right subtree of an AVL tree, then we perform a single left rotation as shown below to make it AVL tree. After inserting node 30, the tree becomes unbalanced. Figure A shows the unbalanced tree. The node 10 has balance factor 2. The balance factor should be either -1 or 0 or 1 in an AVL tree. If balance factor exceeds 1, we need to perform suitable rotations to make the tree an AVL tree. In figure A, node 10 is unbalanced. The unbalanced node is rotated left to make tree an AVL tree as shown in the figure. By rotating node 10 to its left, the tree becomes balanced. After rotation, the balance factors have been readjusted. Now, the tree became a height balanced tree and AVL tree. Figure A shows unbalanced tree. Figure B shows where we are applying left rotation. Figure C shows the height balanced AVL tree. Right rotation. Now let us discuss about right rotation. Inserting nodes 30, 20 and 10 made the given binary tree unbalanced as shown in figure A. To convert this tree into height balanced tree or AVL tree, we need to apply right rotation at the unbalanced node. Observe the tree in figure B. The node 30 has balance factor 2. The balance factor should be either -1 or 0 or 1 in an AVL tree. If balance factor exceeds 1, we need to perform suitable rotations to make the tree an AVL tree. The unbalanced node 30 is rotated right to make it an AVL tree as shown in the figure B. By rotating node 30 to its right, the tree becomes balanced. Now observe the tree in figure C. The balance factors of all nodes have been readjusted. This is a height balanced binary search tree. Figure A shows the unbalanced tree. Figure B shows where we are applying right rotation. Figure C shows the height balanced AVL tree. Now let us discuss about left-right rotation. Double rotations are slightly complex version of already explained versions of rotations. To understand them better, we should take a note of each action performed while rotation. Let's first check how to perform left-right rotation. A left-right rotation is a combination of left rotation followed by right rotation. Inserting nodes in the order 25, 5 and 10 creates an unbalanced tree. To make it a height balanced binary search tree, we need to perform two rotations. Left rotation followed by right rotation. From figure A, if we rotate node 5 to its left, then node 10 comes into the place of 5 and 5 becomes left of 10 as shown in figure B. Balance factors are readjusted. Still it is unbalanced tree. Now rotate 25 to its right so that the tree becomes a height balanced tree, that is AVL tree, which is shown in figure C. Let me explain about right left rotation. Inserting nodes in the order 5, 25 and 10 creates an unbalanced tree as shown in figure A. To make it balanced, we need to perform two rotations. a right rotation followed by a left rotation. Observe the first tree. It is an unbalanced tree. Rotate node 10 and 25 to its right. So 10 comes into 25 position and 25 becomes right node of node 10. Adjust balance factors. Still, we don't get the balanced tree. Now, node 5 has balance factor 2. We have to apply left rotation to node 5 to make the tree an AVL tree. Figure C shows height balanced binary tree, which is AVL tree. Representation of AVL trees. A node in an AVL tree is like a node in a binary tree. Every node contains a key. Every node may contain a left subtree and a right subtree. Moreover, every node in AVL tree should have a balance factor. So, node of an AVL tree has 4 members. Value of the node, left and right subtrees and balance factor as shown in the structure. So, node of an AVL tree can be defined as a structure containing 4 members as shown. Struct AVL node, int data, struct AVL node, left, right, int balance factor. Structure contains data of node, left subtree, right subtree, and balance factor of a node. Now let us discuss about the algorithm to insert a node into an AVL tree. The algorithm has 4 steps. Step 1. First, insert a new element into the tree using binary search tree insertion logic. Step 2. After inserting the elements, you have to check the balance factors of all the nodes. Step 3. When the balance factor of every node will be found like 0, 1 or minus 1, then the algorithm will proceed for the next operation. Step 4. When the balance factor of any node comes other than the above three values, then the tree is said to be imbalanced. Then perform suitable rotations to make it balanced, and then the algorithm will proceed for the next operation. Now, let me explain the construction of an AVL tree by adding nodes one by one using the following example. Construct an AVL tree in the order of key values given as 14, 8, 12, 46, 23, 5, 77, 88, and 20. First step is to insert node 14 into an empty tree. Naturally, it becomes root node. As there is only one node, balance factor of the node is 0. It can be treated as AVL tree. Now add second node with value 8. As 8 is less than root value, it is added to the left of root node. Balance factors of nodes will be evaluated. They are 0 and 1. As the balance factors not exceeding 1, it is an AVL tree. No rotations are needed. Now add node 12. After adding node 12, balance factors also adjusted. We can observe that the tree is not a height balanced tree. As we have already explained, this needs two rotations to make the tree balanced. A left rotation and a right rotation. After left-right rotations, the tree becomes balanced. Next, we insert nodes 46. Balance factors are adjusted. We can observe that the tree is height balanced as the balance factors not exceeding 1. So, no rotations are needed. Now add node 23. Adjust balance factors. We can observe that the balance factors of node 14 and node 12 are 2. Here we need to perform right left rotations to make this tree height balanced as shown in the figure. Then insert node 5. After inserting node 5, the balance factors are again readjusted. We can observe that the tree is balanced as balance factors are not exceeding 1. No rotations are needed as it is already a height balanced binary search tree. Then insert node 77. After insertion, adjust balance factors of all nodes. Observe the balance factors are within the range. So it forms an AVL tree. No rotations are needed. Now insert node 88. After inserting 88, adjust balance factors. It needs left rotation at node 46. Rotating node 46 to its left makes the tree a balanced tree. Then insert node 20. After insertion of node 20, adjust the balance factors. We can observe that the balance factors of nodes are within the range after insertion of 20. So the final tree is an AVL tree. Let me explain another example. Construct a binary search tree with data 8, 10, 3, 2, 1, 5, 4, 6. Then insert an element 7 into binary search tree. Convert the binary search tree into AVL tree using AVL rotations. First create a binary search tree with 8, 10, 3, 2, 1, 5, 4, 6. We get the first binary search tree. Now insert 7 also into the binary search tree so that we get the second binary search tree. Now evaluate all the balance factors. If we observe the balance factors, node 8 has balance factor 3 which is unbalanced. Now rotate it to its right and we get the next binary search. After inserting node 7, we get a binary search tree as shown in figure A or first figure. The node 8 is unbalanced. It is having balance factor 3. Rotate it to its right. You get the next binary search tree which is shown in second figure. Now, node 8 and node 3 having balance factors 2. They are imbalanced. Now rotate 8 to its right. You get the next binary search tree. Now rotate 3 to its left. You get the final binary search tree. After rotation, evaluate the balance factors of all nodes. The balance factors of any node is not exceeding 1, so it forms an AVL tree. Algorithm to delete a node from an AVL tree. Deleting a node from an AVL tree involves three primary steps. Locate the node, delete the node, rebalance the tree. Let me explain these three steps one by one. Locate the node. First, search AVL tree to find node containing the value to be deleted. This search process is identical to searching in a standard binary search tree. Second step, deleting the node. Once the node is found, apply standard binary search tree deletion rules. If the node is a leaf node, simply remove it. If the node has only one child, replace the node with child and delete child. If the node is having two children, find its in-order predecessor or in-order successor. Replace the node's value either with the predecessor or successor and then remove predecessor or successor from its original position. Then rebalance the tree. After deleting the node, AVL tree's balance property might be violated. This is the crucial step that distinguishes AVL deletion from standard binary search tree deletion. Starting from the parent of deleted node, traverse upwards towards the root of the tree. At each node encountered during upward traversal, update its height and calculate its balance factor. If the node's balance factor becomes greater than 1 or less than -1, indicating imbalance of binary tree. Perform appropriate AVL rotations, left rotation, right rotation, or right left rotation to restore balance. This process continues until the root is reached or no further imbalances are found. Let us discuss the process of deleting a node using an example. Let's delete key sequence 654 from the following AVL tree and see how the height balance is maintained throughout. To delete node 6, search for node 6. Node 6 is a leaf node. We can delete node 6 because it is a leaf node. Rearrange balance factors. After rearranging balance factors, we can observe that they are not exceeding 1. So, the binary tree created after deletion of node 6 is an AVL tree. Now, from the binary search tree, delete node 5. Node 5 is having only left tree, not right subtree. It is having only one left child. The value of left child is copied into node 5 and delete left child. Readjust balance factors and check balance factors. If balance factors are not exceeding 1, it is a binary search tree. As the balance factors are not exceeding 1, we got a balanced, height balanced binary search tree. It is a AVL. Now, to delete node 4 from the binary search tree or AVL tree. Node 4 is a leaf node. Leaf node directly can be deleted. After deletion of leaf node, readjust the balance factors. Observe the balance factors. Node 3 has 2 as balance factor, which is imbalanced. So try to rotate node 3 to its right. So rotating node 3 to its right, and after rotation again readjust the balance factors, we can observe that all the balance factors not exceeding 1. So after rotating node 3 to its right, we got a height balanced binary search tree, which is an AVL tree. Let me explain deletion of a node with another example. Delete node 13 from the following AVL tree. Then rearrange nodes as an AVL tree after deleting node 13. The tree which is shown in the figure is a binary search tree. If we observe the balance factors are within the range, so it is an AVL tree. We need to delete node 13. After deletion of node 13, the remaining nodes has to be readjusted as an AVL tree. So first search for node 13. 13 has both left tree and right tree. If a node to be deleted is having both left and right subtrees, find out the in-order successor. So here the in-order successor is 21. So observe the figure 2. 13 is the node to be deleted and 21 is its in-order successor. Now we are replacing 13 with 21 and then we are trying to delete the in-order successor. After deleting in-order successor, again the balance factors of all the nodes are readjusted. If the nodes balance factors are not in range, again we make proper rotations so that the entire tree becomes height balanced binary search tree. Let me explain with in the next slide. We are trying to delete node 13. First we locate node 13. After locating node 13, we check is it a leaf node or is it having only one child or having two childs. In here 13 is having both left and right children. So when a node to be deleted is having both left and right children, we try to replace with in order successor. 21 is the in order successor of node 13. So we replace 13 with its in order successor. That is 13 is replaced with 21. Then we delete the in order successor. After deletion of a node, the balance factors will change. Again, evaluate, readjust the balance factors. If you observe figure C, node 21 is having balance factor 2, which is imbalanced. Now, if you rotate it to its right, we can get the binary search tree, which is shown in figure D. Readjust balance factors. Balance factors are all in the range. They are not exceeding 1. So it is an AVL tree. No rotations are needed. The final figure is a height balanced binary search tree after deletion of node 13.